Hello, today's lecture is Class 8 Optimization 2, R practice. R can do optimization very well. Please check the link at the below. Let's execute this one first. It offers explanation about R. Let's start R. So this is R. It is fine. And then let's practice this one. Optimize is devoted to one-dimensional optimization problem. So if we want to optimize one-dimensional problem, function with one variable, you can use this optimize or optim. I usually use this one, optim. Let me enlarge it. I usually use this one and can use for multi-dimensional optimization problem. So this is very good one. And this is again my preferred one. Okay, let's go directly to the example. One-dimensional problem, the one-dimensional problem. So let me copy and paste this one into, well, our class web page here. So copy and paste this one over here. Okay, and then I have to delete this one, and then basically it defines function. Let me change the line again in R. If we put sharp, then this line computer, the R, the computer, the program cannot read the line starting with sharp. Okay, so this is good for nodes. Okay, so let me delete it, and then this is how we define function with R. So let's look at this. FUNC, here FUNC, this is the name of a function. Here the function is x, basically f x equals x minus 2 square. Okay, so this one. So let's copy and paste this one now in R. Well, it is well defined. Okay, so let's take a look at FUNC and then 3. If we put 3 minus 2 square, so it should be 1, right? How about 4? If we look at the 4, then 4 minus 2 square, so it should be 4. So FUNC 4, right? So again, here, basic FUNC, this is name of the function, i.e. fx. Okay, here the function is fx, x minus 2 square. So we define the function, and then as you know, the shape of this function look like this. Shape of the function looks like Microsoft Paint, and then this is basically we have with this one. Basically we have fx equal x minus 2 square, right? So if we draw the shape of this function, and as you know, the shape looks like this and then this is x-axis. This is the x-axis, and then we have x minus 2 square, so tangent, and this point is 2, right? This is x, basically this is x minus 2 square. So we move this one over here, and this is the x minus 2 square, right? And we know the minimum. Where is the minimum of the function? Well, the minimum happens here, right? This is the minimum. This is the critical point. We know this is the critical point. Minimum, right? This is the minimum. Or critical point. Critical point at x equal to, right? X equal to. X equal to, yes, this looks better. X equal to, and then let's see whether how to get the minimum with R. So let's again go to the example then. Yeah, funds minus 2, well, it's minus 2, minus 2, minus 4, minus 4 squared 16. Okay, so let's try this one. Curve. Okay, this curve. Let's copy and paste this line first into the here, and then let's try curve. Right? So it generates curve, right? This is function. This curve command generate graph plot for this FUNC, name of the function, and x takes the value from minus 4 to 8, and this is the shape of the function, right? So clearly at 2 this takes the value of 0, minimum value, right? And then grid, actually we can use this one as well. Here is the, okay, here is the another way of plot the function using a grid. So first we define grid. Grid is minus 10 value minus 10 to 10 and increase by 0.1. So let's try this one, right? And then paste over here. So type grid. Then as you can see, it starts from minus 10 to 10, over here 10, and it increases by 0.1. Great. And then let's find the value of our defined function at each point in grid. Then, well, we have this value. So for each point in the grid, we get this function. Now we can generate plot. So this plot. Here, this plot. Okay. This first argument is x-axis, and second argument is basically y-axis. So if we do this one, well, this is another graph. So from minus 10 to plus 10, we can see the beautiful graph, x minus 2 square. If you don't like color, actually, you can put color red. Now you have red color. If you want blue, plot blue. Yeah, you have now blue. This one. And then if you find the minimum using the optimization function, so let's try it. Let's try this one. Copy and paste. Again, this one. So you can find the minimum using the optimization function. So we want to optimize function FUNC and interval minus 10 to 10. So between the interval minus 10 to 10, we want to optimize f. Then let's get it. By the way, in many programs, when we get optimized, default is minimum. Minimum is default. Okay. Okay. Usually, minimum is default. Okay. So Well, suppose you want to get the maximum value, then you can simply put minus in front of the function, and if you do the minimization, then it is maximization. So it is fine. Only we can do minimization, right? So let's copy and paste this one in R. Then, well, minimum. Let's take a look at it. Optimize. Then we can find the minimum is 2 and objective is 0. So at 2, it takes the value of 0. If we want only this one or this one, you can do this way. Okay. If you want to pick up only critical points, you can do further following. Okay. Critical point or optimized value, you can do following. So first you define name of this optimization. So let's call this one as a temp. Okay, temp equal temp, and then if you temp, take a look at this, then minimum dollar, there is a dollar in front of it, so you can copy and paste dollar, put over here dollar. This should give the point, critical point, and then objective, copy and paste objective, and this temp over here, temp dollar objective, and this should give the value of the objective, value of objective function at the minimum, at a minimum. Right, so let's try it. Right. Oh, sorry, we have to copy and paste from here. Right, so temp, I define temp, and the temp minimum is 2, temp subject value is 0. This is very, so this optimize, this is very useful. As you can see, this is very useful when you do one variable optimization. Next, Newton-Raphson method. This is interesting, so let's skip. Now let's take a look at this one. BFGS. BFGS is the very powerful method. So, well, if you are interested in BFGS method, you can click this, and then you can, maybe you can want to read what does it mean, what is BFGS, but let's skip. Anyway, let's copy and paste this one again. Next, let us try BFGS. So again, we delete this line. Okay, so function of the name is Fps is same. Now it is like out is x1 minus 2 square, x2 minus 1 square, and we return out. Okay, we don't need this one. And so if we take a look at, so out is returned. So if we take a look at it, this is like, as you can see, this is like, well, f multivariate function. So it is like x1 minus 2 square plus x2 minus 1 square, and we want to optimize this one. Well, it is basically in 3-dimensional. This is basically ball, right? Ball, right? And then if you cut, if you take a look at level curve, it is circle, as you know. So anyway, we know global minimum of this function happens at x equal 2 and x1 equal 2 and x2 equal 1. It takes the global minimum, and let's check it. So let's go to this again, and then this one, copy, paste. So delete, 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 delete. We don't need this one. So here the first argument, there is many arguments. This first argument par equals C00. This one initial point. C par here par equals C00. This is your initial guess. Initial guess. So although we actually know global minimum is x1 equal to x2 equal 1, however, well, to test this one, let's make our initial guess as 0, 0. So basically this program try to find the minimum. This program try to find the minimum starting from 0.0. Okay, starting from 0.0, it wants to minimize it. So optim parameter C0 and fn function func. We want to minimize this function func, right? And gradient null. So well, if you define gradient, this one is actually easy to calculate gradient. You can plug gradient, then it can find the solution much easier. Actually, you can, if you specify gradient as null, then what? It calculates, the program calculates gradient itself numerically and use that value. And method, we use BFGS method and lower bound minus infinite and upper bound plus infinite, which means that when we find the minimum value, minimize the critical point for x1, x2, well, x1 takes any value from minus infinity to plus infinity, and x2 also can take any value from minus infinity to plus infinity. So it means that we don't have any restriction on the search space of x1 and x2. Again, this lower is lower bound for x1 and x2 in searching the solution. Upper bound is upper bound of x1 and x2 in searching for the solution. Control, we can skip it Hessian true. So if you want to look at the Hessian, then you can make it T. So let's try. Copy and paste in R. Enter. Error. Sorry. We have to use this one. So yes, let's look at it. So optim dollar par. So optim dollar par, it is 2, 1. So the value is minimized at 2, 1. Value is basically 10 to the minus power of 26. It is practically 0. So it means that when x is 1 is 2, x2 is 1, the objective function, which is func, takes the value practically 0. And then it takes gradient, it takes basically how many is searched. It is basically describe the path of the searching. You can ignore that. And then we have a Hessian matrix. We already run Hessian matrix, right? And we have a Hessian matrix like this. And then let's take a look at this one. This is basically same. So delete, 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 delete. So this is actually I prefer LBFGS P to BFGS. Okay, so I usually use this one L. The only difference is between this one and this one is we have L and B. Okay, actually I prefer this one. So let's copy and paste, and then voila, we have same answer. Right? Hessian matrix almost the same and everything almost similar. Okay. And then there are other methods. So if you are interested, you can try this one. And we have simulated annealing. Simulated annealing is interesting. This finds the answer with simulation. Okay, so this is same. So let's just copy and paste this one. So simulated annealing and then paste. Then it does basically the same thing, but it finds math with the simulation. Yeah, so it is not exactly 2 and not exactly 1. This is usually true in simulated method. So simulated method is not so accurate around gradient point, but this simulated annealing method, although it looks less accurate, but it is very useful method. If we combine simulated annealing method, this simulated annealing and this gradient search like LPFGSB, we can get very powerful optimization. I will illustrate that shortly. Okay. And then we have genetic algorithm and other thing. If you're interested in, you can take a look at. Okay. And like take a look at our second reference, this one, Optim. Let's click this one. And this is basically more detailed, right? Detailed manual about the general purpose optimization or Optim. Okay, so description, general purpose optimization based on Nelder-Mead, Quasi-Newton, conjugate gradient algorithm integral option for box constraint optimization. So we do some basic constraint optimization and simulated annealing. So you see, so parameter, what is this? It is an initial value for the parameter to be optimized over, and fn is a function to be minimized or maximized with first argument of the vector parameter of which minimization to take place. It should return a scalar result. In the method, we have list of methods. My preferred method is actually this one and this one. I usually combine this method and this method, these two methods to find the solution. And again, lower bound, upper bound. So lower and upper bounds on variable for LPFGS method or bound in which is searchable method in brand. And control, here control, well, it is the list of control parameters, C detail. And Hessian is either true or false, logical, should numerically differentiate Hessian matrix to be returned. Okay? So if you don't want to see the Hessian matrix, you can see false. If you want to take a look at Hessian matrix, you can make it true. Okay? And then there are details, and then, yeah, you can, if you have time, maybe you want to take a look at it. And then here, the control, or at least the control will see detail, about details about this control part, you can't to read this one. There are many, yeah, F and scale here. Right? And step, maxis, sometimes they are useful. But I will skip the detailed explanation about this control list. So let's take a look at the example. Let's go to examples directly. So examples. Okay. First require graphic. So let's require copy and paste require graphic like this one. Require graphic. Let's close this one. You can either click red button over here or you can type div up. And you can close this one. Okay. Here we define function x1, x2. So if you, this name of this function is Rosenbrock-Banana function. So the function is x2. The first argument of x is basic array or factor here. The first argument of x1 is x1. Second argument of x2 is x2, and it returns 100. x2 minus x1 square and 1 minus 1 square. So let's copy and paste this one. Right. So for your FR, let's say 2 and C 2. Okay, it returned the value. The value is 401. Now second gradient. In this case, the name of this is basically 100x2 minus x1 square and x1 minus x1 square. So we can calculate gradient easily. And the gradient looks like this. So this is gradient. So we can define gradient like this one. You know how to get the gradient, right? So GRR is gradient of FR. Now let's do the optimization. Let's use a very simple form. So optimize C minus 1 to 1. So this is again our initial guess for this one. Starting from initial guess of this one find the minimum value of FR. So let's copy and paste this one. Okay, so its minimum value happens at this point and takes the minimum value of 0. Okay, so this is the message, very simple one. Next we can be more specific here. Here in this case we save the result of optimization with earliest here, and then here again our starting value is minus 1.2 and 1, and we want to minimize FR. Here we put gradient here. Now because we calculate gradient, I want computer to use this gradient instead of its own numerical gradient, right? And then computer can do work more easily, more fast. So we plug this on over here, the gradient, and for the math we use Pfds. So let's take a look at, right, and then we can see the answer. So this is actually more accurate over here. This is not exactly 1, 1. By the way, here the minimum value of Rosenbrock banana function is 1.1. Okay, so it exactly found the answer 1, 1, and at point 1, 1 it is practically 0, and we show the answer. Okay, we're using Pfds method. Now this one shows the Hessian matrix. So this shows Hessian matrix, and then I want to take a look at the value of Hessian at our optimized value, earliest par dot par dollar par. So this earliest dollar par, it shows it evaluates function at 1, 1, the minimum, the critical point, and then I want to calculate at this point. I want to calculate Hessian matrix of this one, and we offer gradient. Using this gradient, computer can calculate Hessian more easily. So let's take a look at this one. So yes, we have Hessian matrix. Cool, right? Actually, if you can directly see the Hessian matrix over here. So instead, let's use this one. So again, here, our starting point is minus 1.2 and 1, and we want to minimize FR, and we don't offer gradient. You can write GRR over here, and method is Pfds, and Hessian true. So it returns Hessian. So let's take a look at this one. Copy and paste. Right, and then this is our Hessian. Again, it is almost 1, 1, it is 0, and Hessian is at this point, it is Hessian, and it is basically same to this one. The Hessian we calculated, and this one. Actually, we can try this one, and it's the null. I put GRR. Sorry, GRR. If I use gradient, then it can do calculate even better, right? Instead of numerical gradient, if we supply gradient, analytic gradient, which is better, then it finds that more accurate. And again, but this Hessian is practically same to the previous one, almost same, right? It is almost 400, almost same. And then there are other methods, basically CEG method, and type 2, and then you can check it, and then math error PFGSP. Yes, that's my preferred method. Let's try this one. Yeah, we can get it. It's almost 1, 1. And next, well, this one is slightly more looks complicated. Here, X can be any array, okay? It n-dimensional. You can define the dimension of the vector. So X is arbitrary n-dimensional vector. If you put in n-dimensional vector, first it calculates the length of the vector and the sum from 4 to p minus 1, and x is this one minus c, and then very first one, and then minus p is 1 and square, and it is very arbitrary function. So let's copy and paste this one. Copy and paste this one. paste this one. So define this one. So here we want to optimize this one. So see, first our initial guess is repetition of 325. Let's copy and paste this one. Repetition of 325 times. So it is 3333, like 25 times. It is 25 of the 3. So this is our initial guess. From this initial guess, we want to minimize this function. Now because it is 25 dimensional value, so if we start from this initial value, basically this is a function with 25 variables. Function with 25 variables. So let's see whether this R optim can find minimum value correctly. So here we import. First we have, so starting from this initial value, we want to minimize FLB, and then we don't know for gradient. Maybe we can calculate gradient, but it looks messy, so I don't want to calculate gradient, so null. And method is LPFGSP. And then now we have constraint. So low bound is 2. 2 of the 25. Look, we have initial value is 25 number of 3, so it is 25 variable. So we have basically low and upper bound for 25 variables, right? So for each x, from x1 to x25 basically, our low bound is repetition 22 and our upper bound is 4. So for each variable, we want to find the minimal value, minimized value of this one between 2 and 4 for each variable, right? For each variable. So let's take a look at this one. And enter. Well, now it found the answer. The minimized value is 368, and then, well, minimum value is it is usually low bound, but in this case it is in the middle and it is maximum. So, well, this is so minimized value. So even if we have a complicated function like this one, we can still find it. Now, let's investigate very wild function. Wild function. In this wild function, global minimum is around minus 15.81515. So we already know the answer. And then let's take a look at this wild function. Wow, this is really wild. It looks very wild. Well, we have a sine, another sine, and we have linear part and quadruple part, and then yeah, this FW function. So copy and paste this FW function. This is very wild function. Then why is it wild? Well, it is. Let's take a look at how wild it is. So let's take the look at the graph of this one. So plot. Basically, we want to see the plot of this function FW between minus 50 and 50, and x-axis we have 1,000 degrees. So at 1,000 point, we want to see the graph of this one. So n equal 1,000. So main, this will be the title. This is the title of the graph. So let's copy and paste this one in R. Wow, this is indeed very wild. Here we have this main. This is part is exactly the same to title of this one. Let's enlarge this one. The title, optim parenthesis minimizing wild function. Right? So this is title. We have now title. Okay. This title, this is very wild, and then, well, minimum would be somewhere here, and then if we just do the BFGS or LPFGSB, my preferred one, that is basically gradient search. It takes derivative of the function and put it 0, and it finds the solution. But here we have many critical points, a lot of critical points. So if we just find the value at which first derivative is 0, when it is stuck in many critical points. So in this case, we just cannot find gradient search directly. Ours then, how can you find the minimum value, which is somewhere over? How we can find the minimum? Our strategy is like this. First, we simulated value between the area, and find minimized value over here, and then we find approximately close place. Then we do the gradient search. So we combine two methods. First, we do the simulation to find somewhere close to the minimum value, and then around that point we do the gradient search, basically LPFGSB, and then we found correct, precise minimum point. Okay, so let's do it. First, we do the simulated annealing. So RES opting. Our initial value is 50. Initial value 50. So look, initial value 50. So 50 is somewhere over here. It is far from minimum, somewhere over here, far from here. Well, let's see whether we can find global minimum correctly, even if we start very wild guess, very wrong guess, or like 50 somewhere here, and we say whether from here you can find the solution around here correctly. Well, let's see. So we start from 50, and we want to minimize FW, this wild function, function of wild function, and then we use method, basically simulation method, simulate annealing, and control the maximum iteration and 20,000 times 10 per Pascal. About this one, you can take a look at the explanation above. But let me copy and paste this one. Copy and paste. More. Okay. Copy and paste over here. Okay, and then type less. Then okay. Now it tells that as somewhere minus 15.184181489, it takes the value somewhere here. So it is close somewhere here. So it is now we are close to minimum, but we are not sure it is really the correct point, right? But anyway, this simulation method did this good job. It guided us. It guided us to the minimum point, point close to the minimum, right? So it is good guide. So we want to start from here. We want to start here, and we use now take the derivative approach or gradient approach and find the value one. So we now use the Pfds method R2. So this one, take a look at this one. This one is starts from RES dollar par. It starts from this one RES dollar par is this one dollar par. It starts from here. So this is our initial guess, somewhere minus 15 something, and then we want to minimize this one. Our method this one. So let's do this one. Okay, and it is improved. Previously it is minus 15.8148, and the simulated annealing. Now we have minus 15 about this one, and if you compare this value and this value, this one is smaller than this one. So we have improvement. We minimize it further, all right? And then let's take a point. Let's take a point here. Here. This one is R2 par. This is x-axis, basically this one. Then R2 value, dollar value is dollar value. This is basically at this point the function. This function takes the value of this one. So it is x-axis, y-axis. We want to take a point axis, y-axis, and size of the point, color of the point, something like that. So enter. Then here we have a blue dot around here. Wow, so we really found the minimum point around here, right? So it is cool. Cool. Okay. And then combinatorial optimization, there are other examples over here, and if you are interested, then you can do the practice of this one. Okay, so this is the end of our numerical optimization. I hope you enjoyed this little programming class.